consider the complex number z, which is equal to x plus yi, such that modulus of z minus 2 plus I is equal to 3. Question A shows that x squared plus y squared minus 4x minus 2y minus 4 is equal to 0. So let's consider a given complex number z minus 2 plus I, and let's substitute x plus iy for z to get x plus iy minus 2 minus I, and it is equal to x minus 2 plus I y minus 1 to be clear what is the real part, what is the imaginary part. Why? Because if you don't remember, a modulus of a complex number z x plus iy, the real part, it's the imaginary part, it's just distance from origin, and it's x, it's y, and you can see that it's just right angle triangle, and the required distance from the origin, the required value of modulus is just a square root of the real part squared plus the imaginary part squared. So the modulus of our complex number z minus 2 plus I becomes the square root of x minus 2 squared plus y minus 1 squared, and it is given that it's 3. Then square both sides to get x minus 2 squared plus y minus 1 squared is 9, and then just expand and simplify to get x squared minus 4x plus 4 plus y squared minus 2y plus 1 minus 9 is 0, and it becomes x squared minus 4x x squared plus y squared minus 4x minus 2y. 5 minus 9 is negative 4, so minus 4 is 0 as required. The next, the argument of such a complex number z plus p over z minus 1 is pi over 4, where p is real, and question B shows that it's true. So if the argument of some complex number is pi over 4, it's 45 degrees, 0 is here, in anti-clockwise there are positive angles arguments, in clockwise there are negative arguments, and it's a complex number in the first quadrant, and since this angle is 45 degrees or pi over 4, this triangle is it's a right angle, but here it's important that it's an isosceles triangle, and it means that this length is equal to this length. And what does it mean? It means that the real part is equal to the imaginary part of this complex number, and we will use it. But to equate the real part to the imaginary part, we should clearly understand what is the real part and what is the imaginary part, and our complex number should be given in such form: something without I, real, something real plus I, and also something multiplied by something real without I, and hence we understand that it's the real part is the imaginary part, because now if we substitute x plus iy for z, we get that it's x plus iy plus p divided by x plus iy minus 1. Now we cannot say what is the real part, what is the imaginary part, and we should get rid of y in the denominator. And how to do that? I just rewrite like this, and we just multiply the numerator and the denominator by x minus 1 minus I y to get a formula a plus b multiplied by a minus b in the denominator, which is a squared minus b squared, and it becomes x minus 1 squared minus I y squared, and I squared is negative 1, and hence I disappears in the denominator. So we get x minus 1 minus, but I squared is -1, so plus y squared in the denominator, and just expand the numerator to get x plus p multiplied by x minus 1 plus iy multiplied by x minus 1 minus iy multiplied by x plus p, and this multiplied by this minus, and I squared -1, so it's plus y squared, and it is equal to x squared plus px minus x minus p. And let's factor out iy. It becomes x minus 1 minus x minus p and plus y squared. And it becomes x squared plus p minus 1 x minus p plus y squared, and let's factor out minus here, so it becomes minus iy p plus 1. And now we can see that it's the real part and it's the imaginary part together with minus. And hence we write that since the argument of z plus p over z minus 1 is pi over 4, hence the real part of this complex number is equal to the imaginary part of this complex number. And notice that there will be the same denominator, and when you equate it just cancels, so we can equate without denominator, so it becomes x squared plus p minus 1 x minus p plus y squared is equal to negative y multiplied by p plus 1, so it becomes x squared plus y squared plus p minus 1x plus p plus 1y minus p is 0. Let's check. P minus 1x plus p plus 1y and minus p. Correct. The next two roots of the equation given are z1 and z2, where z1 and z2 are complex, and not real, it's a mistake, are complex, and a, b, c, and d are real coefficients. Both z1 and z2 satisfy the conditions. The modulus of these is equal to 3, so it's absolutely the same as part A, and argument is pi over 4, and you can see that it's absolutely the same as part B, but for P is 4, and hence we get just simultaneous equations. The first directly this, so x squared plus y squared minus 4x minus 2y minus 4 is 0, and the second just substitute the, for p, so it becomes x squared plus y squared plus 3x plus 5y minus 4 is 0, and we should solve for x for y, and z, which is x plus I, y is the solution. It's the required complex number, and there will be two solutions. And let's consider the second minus the first, x squared y squared to disappear, and you can see that it becomes 7x, 3 minus negative 4, 5 minus negative 2 plus 7, y is 0, hence x is negative y. or y is negative x. And then let's substitute, for example, into the first, and let it be in terms of x. So it becomes x squared plus y is negative x but squared, so it's also x squared, minus 4x, y is negative x, so it's plus 2x, minus 4 is 0, 2x squared minus 2x minus 4 is 0. We can divide by 2, so it becomes x squared minus x minus 2 is 0. You may use discriminant or sum and product rule. Sum is minus b over a, it's 1 over 1, so it's 1, and product is c over a, it's negative 2. For product to be negative 2, it's 2 1 and negative 2 or 1, and it's 2 and negative 1, so sum is 1. So x1 is 2, x2 is negative 1. Hence y1 is negative 2 and y2 is 1. Hence z1 is 2 minus 2i, and z2 is negative 1 plus 1i. The next, find the value of a. Question D. What is a? You can see that it is coefficient, and just using a expression which is given in data booklet, and it says that sum of roots of any polynomial, sum of roots is equal to negative a n minus 1 over a n. A n is coefficient in front of the largest power, so a n is this, a n minus 1 is this coefficient, and you can see that it's directly a, and a n is 1. Hence this is given in the data booklet, and it's directly negative a. But what is the sum of roots? We know when a complex number is a root, then complex conjugate is also a root. So if 2 minus 2i is a root, then 2 plus 2i is also a root. And also for this, negative minus 1 plus I plus negative 1 minus I. And you can see that these are 4 roots. It's to the power of 4, so there are 4 roots in total. And it becomes what? 4 minus 2, it's 2, and hence a is negative 2. And that's all for this question.